In this video, we're going to take a look at a few examples of electrophilic aromatic substitution reactions, beginning with nitration. Now, if we take benzene and we react it with a mixture of nitric acid and sulfuric acid, this leads to electrophilic aromatic substitution, where a hydrogen is replaced by a nitro group. Nitric acid plus sulfuric acid leads to the formation of NO2 plus H3O plus HSO4 minus. You don't have to worry about how this works. I just want you to see that NO2 plus is the actual electrophile that's generated. Now let's think about the mechanism of this reaction. Well, benzene can share a pair of electrons with the nitro group, and that pushes these electrons. It doesn't matter whether we go up or down. These electrons get pushed up onto the oxygen, and this leads to this intermediate. So here we still have a hydrogen. This carbon is now a carbocation. This carbon is still connected to the hydrogen that was originally present, and now it's connected to the nitro group, which looks like this. Because we now have an sp3 hybridized carbon, this is no longer an aromatic ring. However, this is still stabilized by resonance. What we have is kind of an allylic system. So we can draw a resonance structure, and let's imagine that these electrons move this way. Now, I like to use the dotted line for the arrows when we're talking about resonance arrows because we're thinking about the imaginary movement of electrons. So this gives us another resonance contributor where we have the double bond here and the positive charge here. We can draw another resonance contributor if we imagine these electrons move this way, giving us this resonance contributor. We can't move any further because now we have an sp3 hybridized carbon. So our pi system can't extend to this carbon, but if we were to draw the resonance hybrid, we have partial double bond character here, 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 and here. We have partial plus at these two positions and this position. So our pi system, while it's not delocalized all the way through the ring, it is delocalized over these carbons, and the partial positive charge is shared. If we focus on where the incoming electrophile is connected, the positions ortho and para to that position, those all share a partial positive charge. So although this molecule has to give up aromaticity to react with an electrophile, it is still somewhat stabilized by resonance. Now let's come back to the reaction itself, and we can imagine that little bits of water that are present, this can act as a base, grab off this proton, allowing these electrons to come back in here and reform the double bond, which reforms the aromatic ring, giving us this as our product. As you're just becoming familiar with these reactions, it's really helpful to go through the mechanistic details. Okay, draw where those electrons are moving. Once we have our intermediate, draw those different resonance contributors. After we have an introduction to electrophilic aromatic substitution reactions on benzene, we're going to look at what happens when we have substituted benzene. And thinking about the resonance contributors is going to be very important to try to determine whether a reaction is going to happen more quickly or more slowly, and whether the product will be installed ortho, meta, or para to the original substituent. So working through the mechanistic details is really, really helpful. Our next electrophilic aromatic substitution reaction is a halogenation. And as an example, we can take benzene and we can react it with bromine and iron, or we could use bromine in the presence of iron tribromide. And what we make is bromobenzene, where one of these hydrogens is replaced by bromine. So when bromine reacts with iron tribromide is a Lewis acid, and so bromine can share electrons with the iron, leading to the formation of a new covalent bond. And there's now a negative formal charge on the iron and a positive charge on the bromine. Even though this bromine bears the positive formal charge, this bromine is actually the electrophilic site. So if we look at the mechanism of this reaction, benzene can share electrons with the bromine, which pushes these electrons onto the bromine with a positive formal charge, which gives us this intermediate. And we have this as our kind of byproduct. And once again, let's take our time to focus on this intermediate, and let's draw the different resonance contributors. Now keep in mind, when you have something with a positive charge, when you are trying to draw another resonance contributor, think about moving the electrons toward the positive charge. But also keep in mind that you want to think of this as a hinge, so that this double bond is going to move from here over here, where these electrons are still associated with this carbon. And then when these electrons move this way, we now have the double bond here, and that leaves this carbon with the positive charge. Again, we want to think about our double bond moving toward the positive charge, and that gives us a third resonance contributor. That looks like this. Also keep in mind, we are using arrows to show the movement of electrons, or the imaginary movement of electrons. We do not show the movement of a positive charge, and we're not drawing arrows to a positive charge, right? That positive charge is just a symbol. We want to imagine the electrons moving to the location where they're going to end up. And then once we have moved those electrons, then we focus on assigning formal charge as needed. In this case, the resonance hybrid is going to look something like this. Partial double bond character here and here and here and here. Notice there is no partial double bond character here or here because, well, number one, because in any of our resonance structures, we do not have a double bond there. But furthermore, it's because this carbon is sp3 hybridized, so we can't have partial double bond character. When we fill in the partial positives, we have a partial positive here and here and here. Once again, ortho and para to the incoming electrophile. Now for the next step of the reaction, we can imagine that bromine decides it no longer wants to share with iron, so it takes these electrons back and then uses a pair to grab off the proton, allowing these electrons to come back in here and recreate the aromatic ring, giving us our final product that looks like this. so that the hydrogen that was originally here is now substituted by the bromine. This reaction can also be carried out using chlorine in the presence of iron, chlorine in the presence of iron trichloride, or it may be necessary to use chlorine in the presence of aluminum trichloride, which is a stronger Lewis acid. There are different methods that can be used to install an iodine, but iodination does not occur with the same type of conditions, but there are other ways to generate an iodine electrophile. And there are some specialized methods that have been developed to create electrophilic fluorine. So for this general set of conditions, this works for chlorination and bromination. There are other conditions that can be used for fluorination or iodination. A third type of electrophilic aromatic substitution reaction is sulfonation. If we have benzene and we treat it with sulfuric acid or with fuming sulfuric acid, which is sulfur trioxide and sulfuric acid, we can form a benzene sulfonic acid. So sulfuric acid itself, it's actually in equilibrium with sulfur trioxide and a bunch of other species. So whether we add it explicitly or we just add this, it's still a source of SO3, which looks like this. And then sulfur is the electrophilic atom. So benzene can share electrons with the sulfur, which can push these electrons up here, for example, leading to this intermediate. So we have our sulfur connected to an O minus, a double bond O, and another O minus. And the sulfur has a positive formal charge. Notice we have more than 4 bonds to sulfur. Because sulfur is in a lower row of the periodic table, it can take on an expanded octet. We can draw additional, and because I was focused on the sulfur group, let's not forget we still have our 1 hydrogen, so that means that this carbon has a positive formal charge. We can draw another resonance contributor that looks like this. And another resonance contributor that looks like this. And therefore our resonance hybrid looks like this. Now when we come back to the main reaction, we can think about HSO4 minus or water could act as the base, grab off this proton, allowing these electrons to fold back in here, and that gives us this, where we're not quite done because we need to think about one more step, which is an acid-base reaction, where one of these O minuses grabs off a proton, giving us, so we have an, oops, sorry, I forgot the plus back here. So one of these is an O minus, one of them is a double bond O, one of them is an OH. And the sulfur still has a positive formal charge. So notice we have a positive formal charge on the sulfur, a negative formal charge on the oxygen. So overall, this substituent is neutral. And normally we would just write it like this. So this is how we form benzene sulfonic acid, okay, a sulfonation. So here we've seen 3 examples of electrophilic aromatic substitution: nitration, halogenation, and sulfonation.